Namaskar and welcome to episode number 1 of Understanding Feynman's Physics podcast. Thank you for joining us on the journey to understand Feynman's worldview, to just try to get a little bit out of it. Um, th- these books are pretty heavy on equations and actually going deep into the mathematics of it, which I won't be able to portray on the podcast because it's just audio. So this is basically going to be an attempt at just showing and conveying and figuring out and finding or just sharing with you some ideas, some new things, some interesting tidbits, some um, facts of about different physical entities, and something that surprises me as well, right? Something that I will find interesting, but we'll try to keep it less heavy on mathematics so a layman can follow while they are walking around, exercising, just like a podcast, right? So y- episode 0 was just an introduction about the motivation and my um, the idea, where I got the idea from, how I got the idea from, and we started with the electromagnetism, and this is just a continuation of that. So this is what Feynman says about um, electromagnetism. There are some very interesting new things that I realized. Well, I already knew that light is an electromagnetic radiation, right? And that's it. I didn't really know much. I still don't know much about it, but I figured out something quite interesting. Where is the? I've been turning pages. Okay, so this is this is how it is. This is what I learned. This is what is interesting about electromagnetism. This is I'll share some interesting tidbits. So there is an important general principle that makes it possible to treat electromagnetic forces in a relatively simple way. Okay, this is whenever we are trying to understand a new phenomenon and try to make sense of it, we need a framework. We need to understand where it lies, how we can make sense of the whole situation. And so in this case, we find from experiment that if you have a positive charge lying somewhere, the force, you can calculate the force applied on that charge just by three things: its position, its velocity, and the amount of charge it holds. All right. Why position? Position Position only dictates the electric and magnetic fields in that position. That's the only reason we are considering position, is because we need to understand what are the electric and magnetic fields at that place where the charge is situated. If we can know that, if we can know the electric and magnetic fields at a position where the charge is, where our charge is, charge A, and we know the amount of charge A, and we know the velocity of this charged particle, we can figure out all the forces, all the electromagnetic forces that are going to be applied there. The force is proportional to the charge, is proportional to velocity, and proportional to the intensity of the electric and magnetic fields. And the equation is Q times E plus Q times VB where V is velocity, B is magnetic field, E is electric field, and Q is the charge. You don't have to worry about it. Just a way to understand how simple this whole situation can be. And this force is universal. No matter how many millions and millions of charges are present anywhere in the universe, in this sandbox universe that we are thinking of, millions is not like billions and billions. All the rest of the charges can be present anywhere, and we don't need to worry about that, except the totality of electric and magnetic fields that are generated by all those charges at this current location. Okay, so if somehow we can understand electric field and magnetic field strength at this location, we can ignore the rest of the charges, because those fields are the only way the rest of the charges are anyways affecting our charge A. So this is a big generalization that we can apply. This is the way we can understand. At least we can try to understand initially. And how do we calculate E? Well, E, the electric field and the magnetic field, they are additive. You get a set of charges. If you calculate the electric field generated by those set of charges, and you get a different set of charges, and you calculate the electric field generated by that different set of charges, the sum of those electric fields, as in the point is, when you have both of those groups of charges placed in the universe at exactly the location where you calculated their electric field through, the resulting electric field is just an addition of those two. Now you might say, of course, this addition, but that's not always the case. That is not always the case with everything. That just turns out to be that in this case, that we just add the amplitudes of different waves. Waves do kind of work like that everywhere. Two waves are superimposed, they get excited, but if the waves are out of phase, they get de-excited. So I'm not sure. I'm not really getting the whole picture here, but this is... So you can kind of calculate the electric field of the rest of the charges. If you were able to calculate that, this would be easy. This is what he writes. Not he writes, but he doesn't write this. He gave lectures on this, and this book actually is a transcription basically of that. So this is what is written. This principle means that if the principle that E is equal to E1 plus E2, the two different fields, this principle means that if we know the law of the electric and magnetic fields produced by a single charge moving in an arbitrary way, then all the laws of electrodynamics are complete. If we want to know the force on charge A, we need only calculate E and B produced by each of the charges, the rest of the charges B, C, and D, and then add the E and B from all of the charges to find the fields, and from then to charge A, right? But as it turns out, this is not easy. Getting this, the resulting fields is not an easy task. In this form, the laws are complex. This is not the best way to show the laws of electrodynamics, electromechanics, magnetism. It is not the simplest to give a formula for the forces that one charge produces on another. That's not the simplest form in which we can understand big systems working on working together. I think this is the same with the gravity. I've heard people say that the three body problem, it's easy to understand how two bodies will, if there are only two bodies in the universe, how will they react with each other gravitationally. But when a third body comes into picture, it becomes more chaotic. You Boundary conditions are a little fuzzy, the chaos theory. Just a little change in input can create wildly different outputs. If, let's say, a comet is coming into the solar system from the outside and it's just a little off, it might go and hit planet A. But if just a little to the left, just even a little to the left, it might go to a completely different planet. These kind of chaos theories, simulations are present online. I might share some link sometime. But it shows us that it's really a complicated way to understand taking all the charges separately and finding the forces on them is not the best way to showcase the understanding of electromagnetism. And this is the crux of this today's episode. The most obvious way is not the only way, and scientists always try to understand how to model things, how to scaffold learning properly so that the resulting facts that come out of it are salient as well as easy to understand. This is, to me, this is a highly creative task. Science doesn't get its due of how creative the whole process is. You are literally trying to, you saw a phenomenon. So there is another podcast that I'm planning to start, which is a little more planned and a little more story like, where I go through the history of science and then try to understand. This has been my goal since long, since it already 10 minutes is already up. This is the ending. I'll just riff a little bit. It has always been my aim since like 3-4 years to have this kind of a podcast where I showcase the start of a scientific field. The first time some phenomenon was discovered, like electromagnetism, and how every person tried to make sense of it from then on. That's fascinating to me. That's interesting. Really interesting. The first time you see magnets interact with each other, you feel like, what the hell is this magic? What's going on? What is this magical force where magnet is attracting iron? Very fascinating. But so just this story of how you see the phenomenon first and then try to understand how will I make sense of it. That process is highly creative. You try one way to do it and you realize the equations that you have are so complex to solve and so hard to understand that you try to then find a different way to do it. And in doing so, you understand different aspects of that same thing. You try different experiments. You set up your experiment to extract new data points to facilitate a theory or to reject it. And every part of that step is highly creative, and you have to think out of the box. You are doing things that no one else has done before. You're thinking things that no one else has thought before. And if that's not the epitome of creativity, I don't know what is. Right? We need to get this out in the open. If you're a creative person, try science, man. Scientific experimentation is fascinating. See you tomorrow.